Okay, for problem 1, it's pretty straightforward. The first one is going to, or part A is just the set that is from 1 to 1/8 to negative 1/8. And then the complement of that, of course, goes from negative infinity to negative 1/8 and 1/8 to infinity. And you could write this using the set builder notation as well, and that would be fine. Now, to do these infinite unions and intersections, it might help to think in terms of a chart here. So let's just go ahead and write down in, and let's see, we'll do the union first. I'll just do this a sub I. And so why don't I do this, just a minute, make one more column. Here's a sub in. Okay, so we have 1, 2, 3, 4, 5, and hopefully we'll see a pattern after that. Okay, so a sub in here is negative 1/2 to 1/2. And then this will be the closed set from negative 1/4 to 1/4. This will be negative 1/8 to 1/8. Negative 1/16 to 1/16. I don't even know if I need to go any further, but I will. Okay, so those are the sets, the a sub n's. Now when we do a union, we're unioning together everything up to this point. So here, this is just this thing, negative 1/2 to 1/2. Okay, this next one, we're going to be unioning together this, and you still get negative 1/2 to 1/2. And then the next one, you're unioning together this, and that, which is still, because negative 1/2 to 1/2 is sort of the biggest of all the sets, it's always, this thing is always negative 1/2 to 1/2. Dot, dot, dot. And so the limit, you can see, is going to be from negative 1/2 to 1/2. Now let's do the intersection of these things. So the intersection, of course, the first intersection, there's nothing to intersect it with. Now when we intersect this with this smaller set, negative 1/4 to 1/4, you actually just get the smaller set. And then when we intersect it with the next one, you can see that it's getting smaller and smaller, but that's the way intersections work. You're always taking off the chunk that isn't overlapping. And so this thing is going to continue, and you can see that, oh, okay, so the limit here is going to be the number 0, because that's the only element that is in every one of the a sub i's. If you tell me a number that you think, like here, let me prove this, that this is it. Proof. If x, which is not equal to 0, is a member of the intersection, then consider, let's see, what do we need to do? The log, how about the log base 2 of x? Okay, so we have the log base 2 of x, and then let's see, we'll do the negative of the log base 2 of x, and we're going to do the negative, how about the ceiling? Whoops. There, this is it, the ceiling. Okay, so then consider this. Let's do k. Well, note that a sub k is going to equal 1 over 2 to the negative ceiling of log base 2 of x. We should probably add 1 to this. Yeah. Plus 1. 1 over 2 to the negative log base 2. And this is negative x. Sorry, it's such a mess. Okay. And I think this should be the absolute value of x in case x is a negative number. But anyway, so consider this set. This set, it turns out that x is not a member of a sub k because x is actually, let's see, x is equal to 2 to the log base 2 of x. You've got this whole sign issue here. Let's just assume, so let's see, if x, where x is greater than 0, how about just make sure that you have a positive number. If it's negative, you could fool around with this and make it work the same way. But anyway, this is the actual value. X is this, because the exponentiation and logarithms are inverse functions of one another. And so that's what x is. And notice what this number is. So this is greater than 2 to the, let's see, this 2. Let's go with that. Okay, and how do we know it's greater? Well, we're dealing with, so we've got the ceiling function here. So we're rounding up, but then we subtract 1 from this. So you end up with a smaller exponent. Which is going to be a and so the actual number will be smaller. But anyway, this thing, so this equals, oh no, this equals 1 over 2 to the log 2 of x minus 1. Okay, I just did that on the fly. Sorry, it's probably not the most efficient way of doing this. And so in other words, so x cannot be in the intersection. Okay, since it's not in this one, it can't be in any of them, or it can't be in the intersection. Okay, well anyway, so that just proves that this is 0, and 0's in all of them. Hopefully you see that that's the case. If not, you can always come and ask me. Okay, this last one, we're going to use De Morgan's law that says that the union of the union of a bunch of complements is the same as the complement of the intersection. And so we can take this intersection, do the complement, which is going to equal the set from negative infinity to 0, unioned 0 to infinity.